MDM4U 3A representing probability distributions. So a probability distribution displays the probabilities for all possible outcomes of an experiment, often shown as a graph of probability versus the value of the random variable. So we have seen the probability for exact values of the random variable that is measured in a probability experiment, but the advantage of a probability distribution is that we can see each of the outcomes and contrast them at the exact same time. So let's look at this example. Consider the following game spinner, which randomly determines the number of spaces a player will advance on their turn. So there's 1, 2, 3, or 4. Notice that they are not equal in size. So therefore, the likelihood, if we are randomly spinning this spinner, isn't going to be the same for each. So what we're going to do is create a probability distribution table and then a probability distribution graph. A probability distribution table has the random variable x, what we are measuring, versus the probability of that outcome. So the outcomes in this experiment are 1, 2, 3, and 4. And the probability of each event, 1 is a half of the circle, 2 is 1/4 of the circle, and if we were to make 8 equal parts, both 3 and 4 are one of those 8 equal sectors. So that being said, the probability, if you add each of these values all together, would be equal to 1 because that's all possible outcomes, and that is a key characteristic of probability distributions is that it spans all of the outcomes that are possible. And therefore, we can compare how likely each of these outcomes are. So this is a probability distribution table. The advantage of this is that we can see the exact numerical value of each and every single probability for each outcome. The advantage of a graph is that we can see visually how likely each outcome is in contrast to one another. So really quickly, a tutorial for Microsoft Excel would include the following. What we do is we enter our table, and I'm going to eliminate this, clicking on it and selecting back to get rid of this graph. Right, cut. Sure. Okay, so what we can do is highlight the area that we wish to graph, click Insert, and then go to Recommended Charts, and you'll see some of the options. We want our random variable x to be those values 1, 2, 3, 4 on the bottom. So this looks like a good starting point. But what we need to include is the following. A title for a graph is typically y versus x. So in this case, y is representing the probability of x versus x, which is our random variable x. So, let's get that keyboard working. Good. All right, so notice that we don't have our labels for our axes, and that's necessary to communicate to anyone reading this graph what it is we're comparing. So when we go to click on our axes, add chart element, axes titles. So primary horizontal, this is the random variable x. We can double click on the text box that appeared. And then similarly, we go to add chart element, axes title, primary vertical. And double click to get all of the text, replace that with the probability of x. And then we have a graph for the probability distribution of x. Going back to our document, what we're going to do is look at the expected value. This is showing us all of the possible values, but we're going to look at what we should expect to happen in a probability experiment. Expected value is an expectation or expected value, denoted E at x, is the predicted average of all possible outcomes of a probability experiment. So the way that this is calculated, if we look at this formula, the expected value of x is equal to the sum of x times the probability of x. This is sigma notation, which just means that we're going to start off with the lowest value of x, whatever the outcome could be, in our previous example, 1, and then we're going to find the probability of that event and multiply it by that value. And we're going to do this. The sigma notation allows us to add each of those different cases together. So we would look at just the next number. So we'll get further lessons on this right here. I'll make sure that that's included. But what is the expected value of the spinner? So what we can do is look at each of those different outcomes. And if we can get the probability distribution table in our window to see how we substitute into this formula. So our lowest value is 1, its probability is 0.5. So we'll multiply those two together. This is 1/2 is 0.5 as a fraction. Plus the outcome, 2 times its probability, which is 1/4. Plus 3 times its probability. And you can prefer to use decimals, fractions. It's up to you. Plus 4 times 0.125, which is 1/8. Altogether, this gives us the value 1.875 as our expected value. So this would mean that if we were to do an infinite number of trials, the average outcome of any particular trial would be 1.875, as we learned with the law of large numbers. And you can see that that is pretty much the point that would balance this distribution here. Notice that these are separate values. And 1.875 isn't something that makes sense as an outcome that you can see from this spinner. That's not an available outcome in the sample space, but it is the average, the statistical middle of the data, the mean. Now, a game is fair if the expected value is 0, meaning in this case we would expect that we would be moving forward. But if there was some risk or some cost to play the game, then we need to assess whether we would be moving ahead or moving backwards or earning money or losing money. So a game involves rolling a single die. You earn the amount on the die for odd numbers, you lose the amount on the die for even numbers. Is this game fair? So what we'll do is apply the expected value formula and look at each of the outcomes. Now the X is the actual outcome to the person who's participating in the game. We said that we earn the amount for odd numbers, so we'll earn 1, 3, 5, and we lose for even numbers, so -2 is the outcome. You lose $2 if you roll a 2. You lose $4 if you roll a 4, and you lose $6 if you roll a 6. When we add each of these together, we get -3/6, which simplifies to -0.5, or that's the equivalent value as a decimal. And we would say that this is not a fair game because on average we would expect to lose on average 50 cents per turn. Okay? So this is not a fair game, and this is how casinos make a lot of their money because the long-term profit is in their favor. And we can say that the game is not fair because the expected value of X is not equal to 0. So we're going to be talking about distributions, and there are different types of variables which we will be analyzing the distribution of. So let's go over some topics here. Raw data is unprocessed information collected for a study. Statistics is the gathering, organization, analysis, and presentation of numerical information. And a variable is a quantity being measured. So we're going to start with this here. We are measuring some quantity in a probability experiment. Now that variable that we're measuring can be one of these 3 types of data. Discrete data, also known as countable. The values are separate. So the number of students in a class and the number of successful trials, these are countable because I could have 0, 1, 2, 3, 4, 5, and so on students in a class. And if I'm doing an experiment and I'm counting the number of successful trials, given that any trial is success or failure, they are whole separate values. I can't have anything between 2 and 3 successful trials. It's either 2 or 3. Continuous data is uncountable. A value exists between any 2 values within a given range. So let's say that a student's height is 180 centimeters and another student's height is 181 centimeters. You can imagine that that 1 centimeter difference between those 2 students has an infinite number of possible values. You don't just wake up the next day and become that next centimeter in height. You assumed every possible value between that interval. And for any 2 points within that 1 centimeter interval, there's still an infinite number of values between any of the 2. So this could be said for weight, time, and length, that they are all continuous variables because for any 2 values within the set that are not equal, there's an infinite number of values between any 2. So here's a challenging one. Think of shoe sizes. For example, 10, 10 and a half, 11, 11 and a half, 12, so on. Is this discrete or data? Discrete or continuous? And the answer is that is actually discrete. Why? Because between the size 10 and 10 and a half, for example, there's no other shoe size that's available for the North American shoe size system. So countable and uncountable is one way of distinguishing between these two types. And categorical data is labels assigned to the outcome instead of numerical data. So for example, color, type, country, names, these are categories or labels. What we're going to be talking about is just one particular type of probability distribution. This is an introduction. It's discrete, meaning that the outcomes are countable. A uniform random variable has an equal probability for each of the outcomes between A and B. So we can think of this as a single trial. And in that experiment, each and every single outcome is equally likely between two values A and B. The probability of each outcome is 1 over n because there's n different outcomes. Let's put this in context with an example. A probability distribution for randomly drawing a number from 1 to 5 from a hat. So numbers 1 to 5 are our outcomes, x, and our probability for each of them is 1 out of 5 because they have an equal chance of being drawn. And notice that this is representing the probability in drawing 1 in one trial. So this is the probability distribution table. This is the probability distribution graph. Notice that a key characteristic is that the probability is equal in value, and that if it's illustrated with a graph, the height would be the same for each. It kind of looks like a rectangle with separate values because it's discrete. The sum of all of the outcomes, so the sum of the probability of x for each and every single possible value of x, as you see expanded here, is equal to 1 because that's all possible outcomes.